Now, let's explore Chapter 7, Stateful Intelligence, Managing Agent Lifecycles with Kubernetes Operators. Now, let's talk about theoretical foundations. The operational deployment of AI agents represents a fundamental shift from traditional request-response microservices to stateful, long-running, and often asynchronous processes. While a standard web API might handle a request in milliseconds and discard its context, an AI agent operates over extended periods, maintains internal state, and interacts with tools, memory, and other agents. This subsection establishes the theoretical underpinnings required to containerize these complex entities effectively, focusing on the architectural marriage between C#'s modern runtime capabilities and the orchestration power of Kubernetes. Let's discuss the stateful nature of AI agents. To understand the operational challenge, we must first dissect the lifecycle of an AI agent. Unlike a stateless function, an agent is a persistent entity. Consider the analogy of a project manager versus a fast food cashier. A cashier, traditional microservice, receives an order, processes it, and immediately forgets the customer. The interaction is transactional and ephemeral. A project manager, AI agent, however, retains context. They remember the project's history, ongoing tasks, dependencies, and the personalities of team members. If the project manager goes home for the night, pod shutdown, and returns the next morning, pod restart, they must resume work without losing the thread of conversation or the state of pending tasks. In C#, state is typically held in memory within object instances. When we containerize an agent, we are packaging this project manager's brain, the runtime process, into a portable unit. However, containers are inherently ephemeral. If a Kubernetes node reboots or a pod crashes, the in-memory state of the agent is lost. Therefore, the theoretical foundation of cloud-native AI agents relies on two pillars. 1. Externalized state, persisting the agent's memory, conversation history, tool execution logs, and planned steps, to a durable store, e.g., Redis, PostgreSQL, or Azure Cosmos DB, rather than relying solely on list T or dictionary T-key, T-value, in memory. 2. Process continuity, ensuring the C# process itself can restart and hydrate its state from the external store, effectively waking up with full recollection. Turning our attention to the microservices boundary for agents. In Book 6, we discussed the actor model, e.g., using Orleans, as a pattern for managing concurrency and state. While the actor model is excellent for high-scale concurrency, cloud-native AI agents often require a broader microservices boundary due to the latency and resource intensity of LLM inference. We treat an agent not as a single object, but as a bounded context, a microservice. This service encapsulates the orchestrator, the C# logic managing the agent's decision loop, planning, reflection. The inference client, the interface communicating with LLMs, OpenAI, Azure OpenAI, or local models. The memory store, the vector database interface, e.g., Pinecone, Milvus, for semantic recall. The why, by defining a strict boundary, we can scale the components independently. If an agent is memory-bound, retrieving vast amounts of context, we scale the memory store. If it is compute-bound, heavy reasoning, we scale the inference client or the orchestrator pods. The analogy, think of a restaurant kitchen. The agent is the entire kitchen station, not just the chef. The station includes the prep area, memory retrieval, the stove, inference, and the plating area, response formatting. If the stove is overwhelmed, high inference load, we don't necessarily need a bigger kitchen, we need more stoves, horizontal scaling, or faster chefs, optimized models. Now, let's talk about containerizing the agent runtime. Containerization in C# is typically handled via Docker and .NET's cross-platform runtime. However, AI agents have specific runtime requirements that differ from standard web APIs. 1. Dependency management. AI agents rely heavily on external SDKs, e.g., Microsoft.Semantic Kernel, OpenAI.SDK, Azure Identity. These dependencies must be locked down in a container image to ensure reproducibility. .NET's global.json and NuGet dependency resolution are critical here. 2. Long-running processes. Standard web containers are designed to handle requests and return. Agents often run background loops, e.g., React loops, reasoning and acting. The container entry point, entry point in Docker, must execute a long-running background service in C#. 3. Resource constraints. LLM inference is memory hungry. A container requesting 2 GB of RAM might crash if the agent loads a large local model, like a 4-bit quantized llama. We must define resource requests and limits explicitly in the container definition. The code concept, theoretical in a standard web app, the program.cs might look like this. Here, we're initiating the build process for our ASP.NET Core web application. Line 1, Web Application.Create Builder, args, is the entry point. It sets up a Web Application Builder object, which is crucial for configuring services and middleware before the application starts. Think of it as preparing the blueprint for your house. The args parameter allows us to pass command line arguments, which can be useful for environment-specific configurations in a cloud-native context, like specifying a port or a configuration file path. Then, at line 2, var app equals builder, build, we finalize the application's configuration and create the web application instance. This app object is what we'll use to define how our application responds to HTTP requests. This pattern ensures all services are registered and ready before any requests are processed, which is a core principle for robust microservices. At line 3, app map get, / equals hello world, we're defining a basic HTTP get endpoint. This is a simple route that responds to requests made to the root URL, / The equals hello world is a lambda expression, a concise way to define an anonymous function that returns the string hello world. In a microservices architecture, this is how you expose specific functionalities. Each microservice would typically have multiple such endpoints, each responsible for a distinct operation, adhering to the single responsibility principle. This minimalist approach is perfect for demonstrating the core functionality of a web API and is a common pattern for health checks in cloud environments. Finally, at line 4, app run, we start the web application. This line is blocking, meaning it keeps the application running and listening for incoming HTTP requests until it's explicitly stopped. In a containerized environment, this is the main process that your Docker container will execute. When this line is reached, the application is fully initialized and ready to serve traffic. This is where the server aspect of your microservice comes alive, making it accessible over the network. Without this, all the previous setup would just be configuration without any active service. For an AI agent, the container entry point is a persistent service. Here, we're defining a background service using ASP.NET Core's background service class. This is a foundational pattern for cloud-native applications, especially microservices, where you need to run long-running tasks that don't directly respond to HTTP requests. Think of it as a worker process within your container, dedicated to continuous operations. This design choice is crucial for decoupling background work from foreground API calls, improving responsiveness and fault tolerance. In a Kubernetes environment, this background service would run as a process within your pod, consuming its allocated CPU and memory resources. This distinction is vital. The container is not just hosting an API, it is hosting a living process. Moving on to orchestration, Kubernetes as the operating system. Once containerized, the agent needs an environment to run in. Kubernetes, acts as the operating system for these distributed agents. The theoretical challenge here is managing stateful sets versus deployments. Deployments, stateless ideal for the cashier analogy. Pods are interchangeable. Stateful sets, stateful required if the agent has a unique identity or requires stable storage, e.g., a local SQLite database for caching. However, most AI agents are hybrid. They are stateless in compute, the reasoning logic, but stateful in data, the memory. Therefore, we typically use deployments for the agent pods and rely on external services, Redis, SQL, for state. The scaling challenge, scaling a standard web app is trivial, more requests equals more replicas. Scaling an AI agent is complex because inference is expensive. Vertical scaling, giving the pod more CPU/GPU, e.g., using GPU nodes in Kubernetes. Horizontal scaling, spinning up more agent replicas. But if 100 users talk to 100 different agents, do we need 100 pods? Or can one pod handle multiple agents asynchronously? This is where Kubernetes native patterns come in. We use the sidecar pattern. The main container runs the agent logic, while a sidecar container handles telemetry, logging, or proxying requests to the LLM. Moving on to inference workload management. The heaviest load on an AI agent is the inference call to the LLM. This is the stove in our kitchen analogy. We must manage this workload carefully to avoid bottlenecks and excessive costs. The batching strategy, LLMs perform best when processing inputs in batches. A single agent might process one user query, but the underlying infrastructure should ideally batch multiple requests to the GPU to maximize throughput. In C#, we can use system, threading, channels or TPL dataflow to create internal buffers. Instead of sending a request to the LLM immediately, the agent queues the request. A background processor flushes the queue every 100 milliseconds or when the batch size reaches 32. The routing strategy, in a multi-model environment, e.g., using GPT-4 for complex reasoning and a smaller model like GPT-3.5 for simple classification, the agent needs a routing logic. Concept, the strategy pattern. Implementation, an I-inference strategy interface with implementation's GPT-4 strategy and local llama strategy. Kubernetes integration, we can deploy different model servers as separate Kubernetes services. The agent pod selects the appropriate service URL based on the complexity of the task. Turning our attention to event-driven communication. Agents rarely exist in isolation. They collaborate. This requires communication patterns that are resilient and decoupled. Synchronous versus asynchronous. Synchronous, HTTP/gRPC user asks agent A asks agent B, agent A waits. This creates tight coupling and potential deadlocks if agent B is slow. Asynchronous, message bus user asks agent A publishes an event, task assigned. Agent B subscribes, processes, and publishes, task completed. Agent A reacts to the completion event. The asynchronous patterns prevent the thundering herd problem where a spike in user traffic cascades through the agent network, overwhelming the inference layer. C# and cloud events. In C#, we utilize libraries like Azure, messaging.servicebus or mass transit to abstract the message broker. The agent logic becomes event-driven. This code snippet presents a theoretical event handler responsible for processing a plan-step-generated event. In a cloud-native microservices architecture, event handlers like this are crucial for decoupling components and enabling asynchronous communication. When an agent, likely an AI agent, generates a planned step that involves using a tool, this handler springs into action. Notice how we define it as async task handle at line 2, indicating that it performs asynchronous operations, which is a best practice for I/O bound tasks in microservices to avoid blocking threads and improve throughput. The plan step generated event, line 2, itself would contain details about the tool to be used and its arguments, acting as a command for this specific handler. This pattern promotes a reactive system where components respond to events rather than tightly coupled direct calls, enhancing scalability and resilience. This aligns with the actor model concepts from previous books but scales horizontally across pods. If an agent pod crashes, the message remains in the queue, if using a durable broker like Azure Service Bus, ensuring no data loss. Now, let's explore resilience and fault tolerance. AI models are non-deterministic. They can hallucinate, fail to format JSON correctly, or time out. The infrastructure must be resilient. Retry policies. In C#, we use libraries like Poly to define retry strategies. However, retrying an LLM call is different from retrying a database call. Transient errors, network retry immediately. Rate limits, HTTP 429 retry with exponential backoff. Content policy violations, do not retry, these are permanent failures. Circuit breakers, if the LLM API is down or error-prone, the agent should break the circuit and switch to a fallback mode, e.g., a cached response or a simpler rule-based logic. This prevents the agent from flooding a failing service. Moving on to theoretical foundations. By containerizing AI agents in C#, we gain portability and isolation. By orchestrating them in Kubernetes, we gain scalability and resilience. However, the magic lies in the internal architecture of the C# code. 1. Interfaces over implementations. Using iChat client or iMemory store allows us to swap infrastructure without changing the agent's core logic. 2. Asynchronous streams. Using iasync enumerability allows the agent to stream responses from the LLM to the user in real time, rather than waiting for the full generation, improving the perceived latency. 3. Dependency injection. .NET's DI container is used to wire up the complex dependencies, strategies, buffers, policies, at startup, ensuring the agent pod initializes correctly every time it scales up. This theoretical foundation moves the AI agent from a prototype running in a Jupyter notebook to a production-grade, scalable microservice capable of handling enterprise workloads. Now, let's talk about basic code example. Here is a self-contained C# example demonstrating a resilient, message-driven AI agent microservice using modern .NET features. We begin by importing necessary namespaces. System, text, JSON is for potential JSON serialization/deserialization, though not explicitly used in this snippet, it's common in microservices. System, threading, channels is crucial for building efficient, thread-safe producer-consumer patterns, which we'll see soon. Microsoft, extensions, hosting provides the infrastructure for building robust, long-running services, especially important for containerized applications. Microsoft, extensions, logging is for structured logging, a best practice for observability in cloud-native environments. Here, we define our domain models using C# record types. Agent message represents an incoming request or task for our AI agent, containing an agent ID, the input string, and a timestamp. Agent result represents the outcome or response from the AI agent. Using record types provides immutability and value-based equality by default, which simplifies data handling and reduces potential bugs in concurrent systems. These are the fundamental data structures that flow through our microservice, defining its API contract essentially. This is our AI Inference Engine class, designed to encapsulate the core AI processing logic. Notice how it takes an iLogger AI Inference Engine in its constructor. This is a prime example of dependency injection, DI, allowing us to inject logging capabilities without tightly coupling the engine to a specific logging implementation. This promotes testability and makes it easy to switch logging providers. The engine itself is designed to be stateless, meaning it doesn't hold any conversational state or user-specific data between calls. This is a critical design principle for horizontally scalable microservices, as it allows any instance of the service to handle any request. The process prompt async method simulates a computationally intensive AI inference task. We log the receipt of the input at line 27, which is vital for tracing requests in a distributed system. At line 30, await task, delay, new random, next, 500, 1500, CT, simulates the time it takes for an AI model to process a prompt. This is a placeholder for actual GPU/CPU computation, network calls to an LLM API, or complex data manipulation. The cancellation token CT parameter is crucial for graceful shutdown, allowing long-running operations to be cancelled when the host requests it, preventing resource leaks and ensuring quick service termination in a container orchestration system like Kubernetes. Continuing in process prompt async, we have a simple mock logic for generating an AI response at line 32. In a real-world scenario, this would involve calling a machine learning model, perhaps through an ONNX runtime, TensorFlow, or a remote API. We log the completion of the inference at line 35, providing another valuable telemetry point. Finally, we return an agent result object. The asynchronous nature of this method, async task agent result, is key for performance in I/O bound or CPU bound scenarios, as it allows the server to handle other requests while waiting for the AI inference to complete, maximizing throughput. Here, we introduce agent worker service, which inherits from background service. This makes it a long-running, non-blocking service managed by the .NET host, ideal for containerized microservices. It also receives an iLogger and our AI inference engine via constructor injection. Observe line 50, where we declare _inbox as a channel agent message. This channel acts as an in-memory message queue, decoupling the ingestion of messages from their processing. This is a fundamental pattern for building resilient and performant services, allowing producers to enqueue messages without waiting for consumers to finish, and vice versa. It's a localized form of message brokering. In the constructor for agent worker service, we initialize our _inbox channel. We use channel.createBounded agent message, new bounded channel options, capacity, 10, to create a bounded channel with a capacity of 10 messages. This is a critical choice for resource management in cloud-native applications. An unbounded channel could lead to memory exhaustion if messages are produced faster than they are consumed. By setting a capacity, we prevent the service from consuming too much memory, which is essential for stable container performance. Full mode equals bounded channel full mode, wait implements backpressure. If the channel is full, any attempt to write a new message will block until space becomes available. This prevents the producer from overwhelming the consumer and helps maintain system stability under high load, a crucial aspect of resilient microservice design. The enqueueasync method serves as the ingestion point for new messages into our agent. It takes an agent message and asynchronously writes it to the _inbox channel using _inbox, writer.write async, message. This method respects the bounded channel full mode, wait setting we configured earlier. If the channel is full, this write async call will naturally pause until capacity is available. This automatic backpressure mechanism is extremely valuable in preventing resource exhaustion. We log a debug message to indicate that the message has been queued. In a real-world scenario, this method might be called by an HTTP endpoint, a message queue listener, e.g., Kafka, RabbitMQ, or a gRPC service, making the internal processing decoupled from the external trigger. This execute async method is the heart of our agent worker service. As an override of background service, this method runs continuously in the background as long as our host is running. We start by logging that the service has started. The await for each, var message and _inbox, reader.readAllAsync, stopping token, loop is a powerful C# feature for consuming asynchronous streams. It efficiently reads messages from our channel. If the channel is empty, readAllAsync will pause without consuming CPU, waiting for new messages. This makes our consumer extremely efficient, only activating when there's work to do, which is excellent for resource utilization in a container. Inside our execute async loop, for each message read from the channel, we enter a try-catch block. At line 89, var result equals await_engine.process prompt async, message, stopping token, calls our AI inference engine to process the message. This again passes the stopping token, ensuring that even long-running inference tasks can be cancelled gracefully during shutdown. After processing, we log the result. The comment at line 92 is crucial. In a production scenario, this is where the result would be published to an event bus or stored in a database. This highlights the stateless nature of the worker. It processes a message and then emits an event or updates a persistent store, rather than holding state itself, which is a core cloud-native pattern for scalability and resilience. Our try-catch block includes specific exception handling. The operation cancelled exception at line 95 is caught when the stopping token is triggered, indicating a graceful shutdown request. We log a warning and break out of the processing loop, allowing the service to terminate cleanly. This is essential for container orchestration systems that send termination signals, like sigterm, to gracefully shut down pods. Without this, ongoing operations might be abruptly cut off, leading to data corruption or incomplete tasks. The general catch, exception X, block is extremely important for the robustness of our worker. The comment at line 104 emphasizes a critical microservice best practice: never let the worker loop die due to a single bad message. If an unhandled exception occurs during message processing, we log the error, but the loop continues to the next message. This prevents a single malformed message or transient error from crashing the entire service, ensuring high availability. In a more sophisticated system, such messages might be moved to a dead letter queue, DLQ, for later analysis or reprocessing, adhering to the fail fast, but recover gracefully principle. This program class contains our application's main entry point, responsible for setting up and running the host. We use host.createDefaultBuilder, args, to get a preconfigured host builder, which includes sensible defaults for configuration, logging, and dependency injection. Inside configure services, we register our dependencies. Services.add_singleton AI inference engine registers our AI engine as a singleton. This is an important architectural decision, since the AI inference engine is stateless and potentially resource-intensive, e.g., loading a large ML model into memory, creating only one instance across the entire application lifetime saves memory and initialization time. In a container, this means the model is loaded once per container instance, optimizing resource usage. Continuing in configure services, we register our agent worker service using services.add_hosted_service agent worker service. This tells the .NET host to manage the lifecycle of our worker service. When the host starts, it will call start async on agent worker service, and when the host stops, it will call stop async. This pattern is fundamental for running long-running background tasks in a reliable way within a microservice, ensuring that our message processing loop is always active as part of the application's core functionality. It integrates seamlessly with container orchestration, which manages the host's lifecycle. We then configure logging using configure logging. Logging.clearProviders removes any default logging providers, giving us full control. Logging.addConsole adds a console logger. For cloud-native applications, logging to STOUT, standard output, is a best practice. Container orchestrators like Kubernetes can then easily collect these logs and forward them to centralized logging systems, e.g., ELK Stack, Splunk, Azure Monitor. This approach simplifies logging configuration within the container and leverages the platform's native log aggregation capabilities, which is crucial for observability in distributed systems. After building the host, we call await host.startAsync. This kicks off all registered iHosted service instances, including our agent worker service. At this point, our worker's execute async method begins running, and it starts listening for messages in its internal channel. This is the moment our microservice becomes active and ready to process work, transitioning from setup to operational state. In a container, this means the container is now healthy and ready to receive traffic. To demonstrate the functionality, we retrieve an instance of agent worker service from the host service provider using host services.getRequiredService agent worker service. This shows how we can interact with our hosted service from the main method, simulating external input. We then print a message to the console, indicating that we're about to inject simulated traffic. This part of the code is purely for demonstration purposes in this example, simulating what a message producer, like an API gateway or another microservice, would do. Here, we simulate concurrent requests by creating a loop that enqueues 5 agent message objects. For each message, we create a new agent message with a unique agent ID and input, then call agentService.enqueueAsync message. We store these task objects in a list. The enqueue call is non-blocking to the main thread because it's an async method writing to a channel. This simulates multiple external clients sending requests to our service simultaneously. This pattern of fire and forget for ingestion, coupled with the internal channel, demonstrates how our service can handle a burst of incoming traffic efficiently without blocking the producers. After enqueuing all the messages, await task.when all tasks ensures that all the enqueue async operations have completed. While enqueue async itself is quick due to the channel, task.when all guarantees that all messages have at least been submitted to the internal channel before proceeding. This is important to ensure our simulation accurately reflects message ingestion. Without this, subsequent steps might execute before all messages are even queued. We then introduce await task, delay, 5000. This is a crucial step in our simulation. Since the worker processes messages asynchronously in the background, the main method would otherwise exit immediately after enqueuing. This delay gives the agent worker service enough time, 5 seconds, to consume and process the messages from its internal channel. In a real deployed microservice, this main method would typically run indefinitely, waiting for the host to be explicitly shut down by the orchestration system. Finally, await host.stopasync is called. This signals the .NET host to begin its shutdown sequence. For our agent worker service, this means the cancellation token passed to execute async will be triggered. Our worker's operation cancelled exception handler will catch this, log the shutdown, and gracefully exit its processing loop. This controlled shutdown is vital for cloud-native applications, ensuring that any in-flight operations are completed or properly cancelled, resources are released, and the container can terminate cleanly without data loss or lingering processes. This is a key aspect of building robust and resilient microservices. Thank you for your attention. This lesson is excerpted from Volume 7, Chapter 7 of the C# and AI Masterclass ebook series and from the volume Cloud-Native AI and Microservices, Containerizing Agents and Scaling Inference. You can find all the details here, https://github.com/edgarmilvas/C# programming series. The ebook also includes diagrams, advanced examples, and 5 exercises with solutions for every chapter. There are 26 chapters. If printed, it would exceed 600 pages. Subscribe to the channel to watch more videos. I look forward to seeing you in the next lesson.